Advanced Graph RAG 2, the next 5 families. Let's dig in. Cast your mind back to the first course, Module 6, and that linear RAG results table. 4 benchmarks across the top, a column of competing systems down the side, and sitting quietly in one of those rows, GFM-RAG. We read the number, we moved on, and not once did we ask what the thing actually was. Today, we open that row, because behind that unassuming baseline label is an architecture unlike anything else in either course. Module 1 broke the assumption that the graph is worth its language model bill. Module 2 broke the assumption that the corpus sits still. Assumption 3 is the one nobody ever says out loud, that a retriever is something you compute and never something you train. Every retrieval mechanism across both courses has been a closed-form algorithm. Not one of them has a single weight that was ever fitted to data. Run the inventory. Personalized PageRank, a damping factor and a fixed-point iteration. Leiden, modularity optimization. Steiner trees, a combinatorial cost minimization. Local semantic bridging, matrix multiplications. Best first search under a budget, a policy you wrote by hand. Every one is a beautiful, deterministic, explainable procedure. And every one encodes a human being's guess about what relevance looks like, baked in permanently before the first query arrives. Here is the distinction in one breath. A computed retriever is a formula. You supply the graph, it supplies the ranking, and the rules never move. A learned retriever is a function with parameters, and those parameters are fitted against examples of what a good retrieval actually looked like. The formula encodes your prior. The model encodes the data's. Which of those two you would rather trust is precisely the argument this whole module is about. Training buys you something no formula can give: the ability to discover that in this domain, this kind of edge matters more than that one, without anybody having told it so. It also bills you. Labeled examples, compute, somewhere to serve a model, and the very real possibility that it simply fails to transfer to your data. Hold that invoice in mind. We'll settle it honestly at the end. We will study 2 systems with very different appetites. GNN-RAG from Mavromatis and Karipis at the University of Minnesota trains a graph neural network to retrieve on your knowledge graph. GFM-RAG from Luo and colleagues at Monash trains one model across 60 graphs and then applies it to yours without touching it. Provenance matters here. The first is an archive preprint marked under review. The second was accepted at NeurIPS 2025. Strip away the mathematics, and a graph neural network does one embarrassingly simple thing. Every node looks at its neighbors, listens to what they say about themselves, and updates its own description accordingly. Then everybody does it again. That is genuinely the whole idea. All the sophistication lives in how you decide what a neighbor says, how you blend the incoming messages, and how many rounds you allow before you stop. Before any of that can happen, every node needs a description to begin with, and that description is a vector. In classical graph learning, it might be a one-hot identifier or a hand-built feature list. In the 2 systems we are about to meet, it is far more interesting than that. The node's starting vector is derived from the question being asked. Hold that thought for a few slides. For now, node in, vector attached. Let us make this concrete with the paper's own example. The question is, which language do Jamaican people speak? Jamaica is our question entity, and around it sits a small neighborhood. English, Jamaican English, the Caribbean Sea, and Haiti, which in turn points onward to French. Watch what a single round of message passing does. Everything one hop from Jamaica hears from it. Run a second round, and French, 2 hops away, finally gets the news. Zoom into a single node mid-round. 3 neighbors each hand it a message, a vector derived from their own state and the relation connecting them. The node piles those messages into one summary, then mixes that summary with what it already believed about itself. Out comes a new vector. Multiply that by every node in the graph, all at once, and you have exactly one layer. Now, the very same thing in symbols, built one piece at a time. The new state of node V at layer L. Its previous state, which we deliberately do not throw away. The message arriving from each neighbor V prime. A weight, omega, which depends on both the question and the relation. Remember that term. It is the star of this entire module. A sum over all neighbors. And psi, the function that combines old self with new evidence. Why a sum and not something cleverer? Because a graph has no row order. Jamaica's neighbors are a set, not a list, and shuffling them must not change the answer by a decimal. So aggregation has to be permutation invariant, a sum, a mean, or a maximum. Sum is the usual choice because it preserves how many neighbors agreed, and that matters when you decide whether a node is well supported or merely mentioned once. The combine step, psi, is where a node keeps its identity. If you simply replaced a node's state with the sum of its neighbors' messages, then after a few rounds, every node would be a blurry average of its region, and nothing would be distinguishable. So psi holds on to the previous state and mixes the new evidence in. In practice, a small neural layer with a residual connection. Memory plus news. Layer count is your reasoning depth. One layer reaches one hop. 3 layers reach 3. Tempting to just crank it up, but stack too many and you get over-smoothing, that blurry average creeping back in globally. GNN-RAG trains exactly 2 variants, shallow at 1 layer, deep at 3. On 2-hop WebQSP questions, the deep network's answer coverage is 88.5% against the shallow one's 79.8%. Here is the idea that makes any of this work for retrieval. That omega term means the message flowing along an edge is scaled by how relevant that relation is to this question. Ask about language, and official language and language spoken swell up, while close to withers away. Ask about geography, and the weights flip. The graph is fixed. The flow through it is question-shaped. That is the largest departure from Course 1. You might expect this to need annotated reasoning paths, somebody marking the correct route through the graph for every question. It does not. The setup is weakly supervised. You get question and answer pairs and nothing else. Answer nodes are positives, everything else negatives, and the network trains as a plain node classifier. The paths it discovers are a byproduct, never a label. That is a very cheap supervision bill. After the final layer, every node carries a vector that has absorbed several hops of question-shaped evidence. A softmax over those turns it into a probability. Is this node an answer, or is it not? So the output is not a ranked list of passages, the way every retriever in Course 1 ended. It is a scored labeling of the entire graph. What you do with that labeling is the next design decision. Compare that directly against Personalized PageRank, which we unpacked at length in Course 1's GFMRAG module. Both of them push signal outward from seed nodes, but PageRank's damping factor is a constant you chose yourself. Its edges are effectively uniform, and it treats every question on Earth identically. The graph network's propagation weights were fitted from data, and they are recomputed for every single query. Same diffusion instinct. One is a physics simulation. The other is an opinion trained on evidence. GNN-RAG's thesis is really a job description. Graph neural networks are excellent at multi-hop structure and hopeless at language. Large language models are exactly the reverse. So stop asking either one to do the other's work. The network becomes the dense subgraph reasoner, which is to say the retriever. The language model becomes the reader. The interface between them is plain text. 5 moves, and then you are done.
Extract a dense subgraph around the question entities. Run the graph neural network over it to score every node. Take the highest scoring nodes as candidate answers. Pull the shortest paths connecting question entities to those candidates. Then verbalize those paths into plain sentences and hand them to the language model. Watch it run once now, and we will take each move apart in turn afterwards.
A real knowledge graph holds millions of facts, and no network is running over the whole of freebase per question. So first, you carve out a question-specific subgraph, link the entities mentioned in the question, then expand outward. And here is a small joke at our expense. That expansion uses the PageRank algorithm. The technique Course 1 spent a whole module on has not been replaced. It has been demoted to the pre-filter the learned part sits on top of.
Before we go near any code, meet the model. GNN-RAG does not invent a new architecture. It reuses ReaRev, an earlier graph network by the same authors, built for deep knowledge graph reasoning. It is embedding-based, chosen precisely because it explores diverse reasoning paths, and therefore has high answer recall, which is exactly what you want in a retriever, where missing the answer is fatal, and extra candidates are merely untidy.
Once the layers have run, every node carries a probability of being an answer. Thresholded. Nodes above the bar become candidate answers, and everything else is dropped on the floor. Now, notice what has just happened. The retriever has produced an answer set before the language model has read a single word. That is unusual and faintly unnerving. But the candidates are not the deliverable. They are the anchors for the step that actually is.
Here is the move that turns a node classifier into an actual retriever. Take every question entity, take every candidate answer, and extract the shortest path between them through the graph. Jamaica to English by way of official language. Jamaica to Jamaican English by way of language spoken. Those paths are the evidence, not merely what the answer is, but why it is the answer. And unlike a node score, a path is something you can write down in words. Verbalization is almost insultingly simple. Verbalization is almost insultingly simple. Question entity, arrow, relation, arrow, entity. Onward to the answer. 4 short lines of text for our Jamaica question. Those lines drop into a fixed prompt. Based on the reasoning paths, please answer the given question, along with the question itself. The graph has become a paragraph, in the only format the reader speaks.
Let us open up that omega weight properly. The question and the relation are each encoded by a shared pre-trained language model, attention pooling for the question, CLS pooling for the relation. The two are then multiplied element-wise, and a small neural network squashes the result to a single scalar. 2 representations meeting in one space, agreement measured coordinate by coordinate. The paper trains 2 versions, one on SBERT and one on a knowledge graph-specific encoder. Second tool stop, before any code. The repository, cmavro/GNN-RAG, splits into 2 folders. GNN, holding the graph network implementations, and LLM, holding the retrieval augmented generation side. The reader is a Llama 2 Chat 7 billion model, fine-tuned on the training question and answer pairs. Helpfully, pre-computed network outputs ship with it, so you can reproduce the language model half without training anything.
Now, the whole chain in one place. Link the question entities and extract the dense subgraph. Load the trained network and run a forward pass to get node scores. Threshold those into candidates. Extract the shortest paths from question entities to each candidate. Verbalize them and build the prompt. Call the tuned reader. And then the optional last step, retrieval augmentation, takes the union of these paths with a language model generated set before prompting. State-of-the-art on both WebQSP and complex web questions. With retrieval augmentation, an F1 of 73.5 and 60.4, and between 8.9 and 15.5 F1 points over competing methods on multi-hop and multi-entity questions. It matches GPT-4 with a tuned 7 billion reader on a single 24 gigabyte card against an estimated $800 of GPT-4 calls. But on one-hop questions, the language model retriever wins. Depth was never free. Everything so far trains a retriever for one knowledge graph. Build a second corpus, and you train all over again. That is exactly the pattern foundation models demolished everywhere else in machine learning. And GFM-RAG asks the obvious question, why not here? Pre-train one graph model across a large collection of knowledge graphs, and then drop it, untouched, onto a graph it has never seen before. No fine-tuning, no labels, no training run at all. That is much harder than it sounds, and it is worth understanding why. Two corpora share almost nothing. Different entities, different relation vocabularies, different graph shapes. A network trained on a biomedical graph has learned weights indexed to relations like binds to. Handed a legal corpus full of party to and supersedes, and those weights are simply meaningless. Language models solve this with shared tokens. Graphs had no equivalent, until somebody noticed that relation names are also words. And that is the whole unlock. GFM-RAG encodes the query, the entities, and the relation names with the same frozen sentence embedding model, all MPNet base v2. A relation the model has never seen is no longer an unknown index. It is a sentence, and sentences live in a space it already understands. Nothing is tied to a vocabulary. Swap the graph, and every input still lands somewhere meaningful. New example now, because the task itself has changed. We are retrieving documents, not entities. Barack Obama is the politician of which country? 4 documents become a knowledge graph index. The query initializes the entities it mentions. Query-dependent message passing then spreads relevance across the graph. Every entity gets a score. A document ranker converts those entity scores back into document scores. The top documents go to the language model. One single pass, and it is genuinely multi-hop. The index has 3 parts, and only the first is obvious. 1. Open information extraction pulls triples out of the documents, which gives you the graph. 2. An entity-to-document inverted matrix records which entity appeared in which document, and that is the bridge you walk back across at ranking time. 3. Entity resolution adds equivalence edges, so USA and United States of America stop being strangers. The equations are where this really differs from a textbook graph network. Entities named in the query are initialized with the query embedding itself, and every other entity starts at exactly 0. So the query is not a side input to the model, it is the initial condition. Messages then propagate over triples, entities update, and after the final layer, a small network plus a sigmoid turns every entity's vector into a relevance score between 0 and 1. Stage 1 is self-supervised and needs no annotation whatsoever. Take a triple, hide either the head or the tail, and ask the model to predict what you hid using the rest of the graph. That teaches graph reasoning essentially for free. Stage 2 is supervised, real questions with the entities drawn from their supporting documents as the targets. Stage 1 teaches it how to walk a graph. Stage 2 teaches it how to walk toward documents. The pre-training corpus is what earns the word foundation. 60 knowledge graphs, over 14 million triples, 700,000 documents. And the model itself is almost comically small. 8 million parameters, 6 message passing layers, hidden dimension 512, trained on 8 A100s. 8 million. Your sentence encoder is bigger than your foundation model. The capacity that would have memorized vocabulary was outsourced to that frozen encoder. You have scores on entities, but what you need is documents. So take the top scoring entities, then weight each by the inverse of how many documents mention it. A popular entity is weak evidence. A rare one is strong, which is really just inverse document frequency wearing a graph costume. Multiply through the inverted index, and every document inherits a score. Take the top K and hand them over. Tools stop before the code. Pip install GFM-RAG gives you the package. You point it at a data directory containing documents.json, and it builds the index for you using a named entity model, an entity linking model, and a graph constructor. Or if you already have nodes, relations, and edges as CSV files, it skips construction entirely. Pre-trained checkpoints live on Hugging Face, the 8 million parameter model, and a larger successor. The complete pipeline, and it is startlingly short. Put your documents in place. Construct the retriever from the index, naming the checkpoint and the construction components. Call retrieve with a query and a top K. Get back ranked documents. Then feed those, along with the question, to whatever language model you like. There is no training call anywhere in this listing. That absence is the entire contribution. One last piece of evidence, and it is the one that most justifies the word foundation. Fit the model's retrieval quality against both training data volume and parameter count, and you get a clean power law with an R-squared of 0.95. More data helps, more parameters help, predictably. That is precisely the property that turns scaling language models into a strategy rather than a gamble. Though, do note how small those exponents are. NeurIPS 2025, so this one is peer-reviewed. Recall at 5 of 87, 58, and 95.6 on Hotpot QA, MuSeek, and 2Wiki, beating a multi-step pipeline while doing only single-step retrieval at roughly 1/30th of its latency. And on 7 domain-specific datasets it never saw in training, with 0 fine-tuning, it improves on HippoRAG by around 19% on average. That last sentence is the real headline. So let us settle that invoice. Inductive bias. A formula encodes your guess. A model encodes the data's. Data cost, 0, versus question-answer pairs or somebody else's pre-training run. Generalization. An algorithm works anywhere immediately. A trained model may not travel. Latency. Comparable, sometimes better. Debuggability. You can read a shortest path, and you cannot read a weight matrix. Cold start. The algorithm wins outright, every single time. Be honest about this one. If your corpus is small, if your questions are single-hop lookups, if you have no labeled question-answer pairs and no appetite for building any, or if you must explain to a regulator exactly why a document was retrieved, then Course 1 already gave you the better answer, and it costs nothing to serve. Personalized PageRank over a decent graph is a very hard baseline to beat. Worth separating these clearly, because the names really do invite confusion. GNN-RAG answers questions over a curated knowledge graph and returns entities, classic knowledge graph question answering, trained per graph. GFM-RAG retrieves documents from a corpus whose graph was extracted by a language model, and it is trained once for everything. Different tasks, different outputs, different economics. They share message passing, and almost nothing else. Module 1 handed us a 4-point lens, so let us use it. GNN-RAG, an archive preprint, still marked under review, but evaluated on 2 standard public benchmarks with released code and pre-computed outputs, reproducible if unreviewed. GFMRAG, peer-reviewed at NeurIPS, with a genuinely impressive zero-shot claim, but the authors chose those 7 transfer datasets themselves. Neither has been measured on GraphRagBench. So what do you actually do on Monday morning? If you already have a knowledge graph and real question and answer logs, A trained retriever is now a reasonable line item, and GNN-RAG's recipe is a good template. If you have documents and no labels, try the pre-trained foundation retriever before writing a line of training script. It costs an afternoon. Neither of those? Stay algorithmic and spend the money on your graph. So, retrievers can be trained, and one of them has already been trained for you. That is assumption 3, gone. Assumption 4 is stranger still, that knowledge arrives in binary triples, one subject, one relation, one object. Next module, we meet hypergraphs, atomic facts, and tree structures, where a single relationship can bind 5 things at once. The graph is about to stop being a graph. See you there.
If you like this video, please subscribe and share. Thank you.